All right, a few more people are going to filter in, and absolutely feel free to get some food and refreshments while you're here. So I just want to introduce our speaker. This is Simon Du from the School of Computer Science and Engineering at the University of Washington. He's also an alum of Carnegie Mellon. Got your PhD here in 2019.
Yeah.
So he's very familiar with the CMU scene. We're happy to have him here. He's working on one of the projects in our foundational thrust. And so he's going to tell us a little bit about offline multi-agent games today. And so welcome, Simon.
All right, thanks for the nice introduction. It's always nice to be back. So today I'm going to talk about our recent work on offline multi-agent games. All right, to motivate the offline reinforcement learning, I think many of you are kind of familiar with the reinforcement learning basic setup. Basically, we are controlling an agent with a robot here, which is interacting with an environment. Okay, and then during the interactions, we gather data, and then we try to improve our performance of this agent. So many times we just train, let's say, a neural network, and then we interact with the environment with new policy, and we iterate. So that's a standard reinforcement learning, or more specifically, the online reinforcement learning setup. The offline reinforcement learning is different. We try to learn or output a good policy just using the offline data, collected from some prior experience or interactions with the environment. Okay, so for example, here, we just gathered a lot of big data set from the past interactions, and then we just use this data set to get a policy. Okay, we can still train a neural network, and that's offline reinforcement. Basically, we do not have the capability to further interact with the environment. Okay, so generally speaking, we have lots of offline data from prior experience. The motivation that usually fresh samples are very expensive, especially in those high-stake domains like medical domains, recommendation system, etc. So this talk, we talking about the theoretical foundations for offline reinforcement learning. And basically, we want to study when we can find a good policy from the offline data. So here's just one motivation for offline reinforcement learning is in medical domains, where you have some treatment for the patient, and you collect some past data from different patients. And it's very hard or very costly to do experiments on new patients. So we try to use the offline data, the past experience data, as much as possible to develop the new, let's say, optimal treatment. So that's one of the major motivation for offline reinforcement learning. All right, so that's sort of the motivations. And let's discuss what is set up here. So this is a standard single agent reinforcement learning. So to put in some rigorousness, so we have an agent interacting with an environment. So it has several time steps. Okay, so as time step t, the agent is at the state st, and this agent will take some action at based on the state st. And then the environment will move the agent to the next state, st+1, according to transition probability, let's say this pt given st and at. And also the agent will receive some reward based on st and at as well. And then this interaction repeat for h times. That's one episode, or we also call this h the planning horizon. So this is a standard single agent reinforcement learning setup. All right, so a couple of more important notations for reinforcement learning. So how do you choose the action? So the agent will choose the action according to policy, which is a function that maps the state to an action. Okay, so A equals to pi s if the pi is deterministic. And the goal of this agent is to maximize the value function, or basically the total reward this agent can receive throughout the trajectory. So since there will be some randomness in it, it's an expectation over all the randomness in the environment. So it's a the value function of the initial state S1 is just the total reward throughout the trajectory. Okay, in expectation. And our goal for this learning problem is to learn a near optimal policy. Okay, so we try to find a pi, okay, which is our policy. First, we output this pi, its value, v pi s1 is very close to the optimal value function of the maximum possible expected reward you can receive. So here, v star here is the total expected reward of the optimal policy. And here, epsilon is just some target accuracy we want to achieve. Okay, I hope the setup is clear for the single agent reinforcement learning. All right, so throughout the talk, I'll mainly focus on tabular setting. So this is arguably the simplest setting. You have a finite number of states, finite number of actions, and say reward is from 0 to 1. And generally speaking, this sample complexity will depends on say polynomially on the number of states, number of actions, the planning horizon, and the target inverse of the target accuracy. So this is kind of the most basic fundamental setting in reinforcement learning, and there are a line of work try to generalize the setup to function approximation or to infinite many states. But the many insights just from the tabular one can be generalizable. And here we'll just focus on the tabular one. If we're interested, we can discuss more offline for the large state space problems. All right, so what is the offline problem? Okay, so offline problem, we first have a data set collected with some distribution or with some policy. So this is the formal setup. So we have data set of this kind. Okay, so it's D here. So it has state, action. So each data point in this data set is a tuple. Each tuple is a state, action, and reward. And in total, let's say you have n trajectories, okay? And remember, in each trajectory or in each episode, you have h steps. So in total, you will have this number of data set points, okay? So h is from 1 to big H, I is from 1 to n. So in offline reinforcement learning, we just assume we have this data set sampled from some behavior policy row. Okay, this is called data collection or behavior policy. So given this policy, it will induce a distribution over the state, action, and reward space, and that gives you this data set. So basically, we just sample from this distribution D row. Okay, the D row will depend on the policy and also the transition and the reward as well. So the goal of offline reinforcement learning is to learn a policy from this data set such that it's near optimal. So we output the pi just from this data set such that the v pi of S1 is close to the optimal policy. So theoretically, one natural question is, under what conditions on this distribution that generates data, you can actually learn a near optimal policy. So that's kind of different from the supervised learning, where if your task distribution and training distribution, they are the same, then basically, as long as you have enough data, then you can learn the near optimal predictor because you can just generalize it. But here, one important difficulty in reinforcement learning is that the policy that you actually deploy will generate a different distribution than the one you actually collect the data. So you do need additional assumptions on the data collection policy so that you can argue the policy you learned is actually near optimal. So one natural question is like, what kind of condition we really need? So in the literature, back in the day, one natural assumption is called uniform coverage assumption, which says that the behavior policy, this data collection policy, covers every state action pair. So you have data from every state action pair. So formally, you have this condition. So there exists some constant C uniform such that this density ratio, 1 over this density or probability mass function of the state action pair induced by the behavior policy rho is upper bounded by this constant. Right? Basically, it means that for every state action pair, you have some minimum reaching data collection probability. Okay, so since we know that in total, let's say you have S states and A actions, and since you have uniform upper bound for this inverse, then we know that C uniform is at least S times A. If you have a number of states being S and number of actions being A, and if it's also possible that it's infinity if you do not have data from certain state and action. So, but if you have this condition and say UC uniform is finite, what you can do is just you just estimate, use empirical data to estimate the transition, which is a P, and estimate the reward R, and then based on this estimated reward and probability, you just do a planning step and then output the best policy from this empirical estimate. Okay? And that's the algorithm. To compute this optimal policy, you just use dynamic programming, which is standard way in reinforcement learning. So in this setting, we pretty much settles the sample complexity. It's scale in this form, it's h to the cube and times the C unit for epsilon square. So that's a tight sample complexity bound. All right, so this is for the uniform coverage assumption, which is quite strong because it requires you touch every state action pair. So natural question is, do we really need a strong assumption of the data? Like, can we relax it? So here's comes the next assumption, which is called single policy coverage assumption. So at the high level, because you only want to learn the optimal policy, so you expect that as long as our data contains the trajectory of the optimal policy, this should be enough to kind of recover this policy. And this is precisely what this assumption says. So the behavior policy only covers a single optimal policy. Okay, and you can show that this is both necessary and sufficient conditions. So formally, let's say there exists some constant C single, okay, such that this density ratio between the optimal policy, between the distribution of the optimal policy, which I denote as d pi star of every state action pair, divided by this density function or the mass function of the data collection policy rho. So for every state action pair, it is upper bounded by this constant. Basically, for every state action pair that has some probability mass induced by the optimal policy, you also have some probability mass for your data collection policy. That's the intuition. Okay. This assumption was like formally studied back in 2019, and you can see here. Suppose rho that equals to pi star, then the C single equals to 1. So this constant can be much smaller than the C unit in the best case. Okay. On the other hand, you do need to change your algorithm to really make it work. You can not just naively estimate the transition and reward and then output the optimal policy for that. Here you need some new algorithm idea called pessimism. It has also been tested empirically, which is also very useful. And in theory, they're lining up for basically showing this is, this algorithm based on pessimism is minimax output up to for sample complexity. And we can also derive some instance dependent bounds for using pessimism. So the key takeaway here is that this is like necessary and sufficient condition. And let me briefly introduce what the pessimism is. Okay, so let's say here's a very simple setting. Let's say we just have 4 actions. You can think of it as a bandit problem, and we have, say, each one has its own value. So basically we have the offline data, and we have our estimation for the mean of each of the action. Okay, so QA, QB, QC, QD is our estimation, the mean. So using pessimism, we not only use the mean, okay, our estimation of the reward, we also use also build a confidence interval for our estimation because there's some randomness in the data, so our estimate is now never entirely correct. We always have some estimation error, but we can use the data set to build a confidence interval for each of the action module. So for example, here we have maybe we have less data for action A, so we have a large confidence interval because that's we have less data, but we have a higher like tight confidence interval for action B. So we have confidence interval here. It's the length is shorter. So by pessimism, basically we choose action. Okay. So what's the optimal? What's the output of our policy? It will be the action with the highest lower bound. Okay, that's why we are being pessimism. So we actually here in this example, we'll choose action B because it has the highest lower bound. So we are very conservative. So because if we choose here, we can guarantee that we can at least get this amount of reward. Whereas if we choose, say, action A or D or C, like although it's at like mean reward, our estimation is higher than B. In the worst case, it can be very much lower than action B. So being conservative here help us to reduce the uncertainty and actually theoretically can show this is necessary to get the tight, to get the really output the near optimal policy. Yeah.
Could you maybe provide some intuition as to why pessimism is necessary here, but in the previous setting it's suffice to consider the empirical?
Yeah, so that's a great question. So in the uniform coverage condition, if you have enough data, it means that you have, basically for every city action pair, you have a lot of data. So you will have something like for every state action, you will have very tight confidence bound. But here, let's say you have one action that is not optimal, and you have very little. It's possible you have very little data, or even have no data because it is, for example, here suppose one action that is not optimal, then this constant, then you may not cover that action, right? Based on this assumption. So for that, you have not have any good estimation for that. So here you will be very conservative, then your confidence interval will be in the bottom, and so you will not choose that action. So that's conservative or pessimism kind of guarantees you choose a near optimal action. All right, so that's the idea of pessimism, and that's a basically whole idea of offline single agent reinforced learning, and we have a pretty good understanding like what is needed for single agent reinforced learning, and then we have an efficient algorithm for it. All right, so the main topic today I want to talk about is on multi-agent reinforcement learning. It's becoming more and more popular nowadays. So we can model the competitive games like Go, cooperative robots, and in our AI-SDM Institute, it naturally model a lot of applications for societal decision-making problems. Okay, so at high level, multi-agent reinforcement learning is that a setting where multiple agents operate in a common and unknown environment. And each agent aims to optimize. So each agent has its own long-term return or the value function it wants to maximize. But the challenge here is that the environment is not exactly fixed from a single agent point of view because the environment will kind of change or from single agent view according to other agents' actions. So it's like a kind of dynamically changing environment from a single agent view. That's a challenge. So today I'm going to talk about several settings in multi-agent reinforcement in the offline setting, and we'll show that it will require significantly different assumption. It has a data set assumption from the single agent setting. So let's start from the simplest one, simplest setting in multi-agent reinforcement, which is a competitive game, two-player competitive or two-player zero-sum Markov games. Okay, so in this setting, you have two players. They are compete against each other. Each has a strategy, so it naturally models like games like Go or poker and some other computer game investments, etc. And the goal here is to find a Nash equilibrium. So in multi-agent, by optimality, we want to find a Nash equilibrium. So what is Nash equilibrium? Nash equilibrium basically is a pair of strategies such that no player can do better to achieve higher reward by unilaterally changing the policy. Okay, so if you have a pair of policy, and if no matter what policy one player change, it will not get higher reward for that agent. That's Nash equilibrium. Okay, so specifically this is a setting. So it's very similar to a single agent setting, but here we have two players. So again, we have two players interacting with an environment, each one at each time step, they are in a state, ST. Different from single agent setting, here you have an action pair, AT and BT, okay? So both players choose an action, and the environment will send transit state to the next state according to the transition probability, which depends on the current state and actions of both players. Also, it will reveal some reward to the agent. So in this setting, and of course, you will repeat for each time, each is the planning for it. So you have two players. For the zero-sum setting, you have one player being called max player, who tries to maximize the reward. So the goal of this max player is to try to maximize the expected total reward. And there's a min player who tries to minimize the total reward. So that's why they are competing against each other. So our result holds for this zero-sum Markov games, but to provide the main insight, I will mainly focus on a much simpler setting, which give you the core ideas of this zero-sum setting, which is just a zero-sum bandit. Okay, so here h equals 1, so you only don't need to consider the transition anymore, and there's only one state. The only thing that matters is the reward. Basically, every episode, you like both players choose an action. One tries to maximize reward, one tries to minimize reward. Okay, and we'll mainly use the zero-sum bandit as an illustrating example to show our main technical ideas. Okay. Yeah. Yeah.
If one wants to maximize and one wants to minimize, isn't that trivial? One takes all the payoff, the other takes none of the payoff, and everybody's happy.
So the reward is not known to the both players, so you need to learn it. And I mean, they are competing against each other, right? So and this reward depends on both players' actions. So you cannot simply take the payoff. Like I choose an action, you choose an action, and then the reward. Then we see the reward. So you cannot really collaborate. It's like competing against each other.
Okay, it seems like if they both wanted a lot of rewards, that would sound more competitive, right? They can't both have a lot.
Oh, so the reward can be negative and positive, if that's help you understand. So max player try to maximize the total reward, where min to minimize the reward. But the reward are shared, of course. Then they receive the same reward. They got the same reward, but one want to maybe the reward is not the correct word, but one base, yeah.
The reward is joint.
Yeah, the reward is the same. It's foreign for both, so they're still competing against it. Yeah. Thanks for asking. Yeah.
Also note that there is a slight difference between this setting and the real case. Because, for example, if two players are playing Go, then after the first player makes his decision, he already knows whether his decision is good or not. So partially knows.
Yeah, that's a good point. So let me be more clear. So here, this is you should call this simultaneous move. Like they are at the same time they choose actions. Where in Go is like a turn-based game. Like I choose action, you choose action after I choose action, and then we repeat. So that's a slightly different setting, although the results can be generalized to turn-based game as well. All right. All right, so generally speaking, we still study the tabular setting. We have finite state, action, horizons, and some more complexity will, depend polynomially on the number of state, number of action for both players. finding horizon, and the target accuracy 1 over epsilon. All right, and again, we studied offline setting. Okay, so we have an offline data set just like before. It's just now we have a slightly more complicated data points. So now each data point, we have one more action because we have 2 players. So in each data point, you have the current state, a pair of action A and B, and the reward, which is shared. And they are sampling from the data set is sampled from some distribution. D rho. Okay, rho is data collection or the behavior policy. So again, this distribution is induced by this data collection policy and the transition probability of this game. And here the goal is to learn a pair of policy, a policy pair mu and nu, such that they are like epsilon close to a Nash equilibrium. So that's like a near epsilon close Nash equilibrium. All right, so again, we just ask this natural question: under what conditions on this distribution, or basically this behavior policy, we can actually learn this an epsilon close Nash equilibrium? Okay, so that's a kind of foundation question you may ask in the first place, like when we can actually learn a Nash equilibrium. All right, so the first proposal here is that we again consider we call single policy pair coverage, which is a natural generalization of the single policy coverage. Remember, single policy coverage just means that the density ratio between one optimal policy and that of the probability density of the behavior policy is upper bounded. And here the natural generalization is just you have a pair, policy pair, say mu star, nu star. Let's say they are a Nash equilibrium, okay? And given that pair, you will induce a policy. They will induce a distribution. It's called D. And you have your own behavior policy or data collection policy pair rho. So the natural generalization of the single agent case here is that this density ratio is upper bounded by some constant, right? And you hope that your sample complexity will depend on this constant. Okay, that's a natural generalization. So our first result on this setting is that actually we show that this is not enough. Okay, so this natural generalization from a single agent is not enough to learn a Nash equilibrium even in the simple 2-player zero-sum game.
Simon, there's a question in the chat.
Okay.
It says, are we assuming Markovian policies?
Yes, throughout my talk is a Markovian policy. Yeah, so the question is, are we assuming Markovian policy? And yes, we are assuming Markovian policy. And actually for this setting, you can show that optimal policy is Markovian because we are considering Markov games, and there's no partial observability there. All right, so why this is not enough? So this is a very simple example to illustrate the main idea, and we believe this might be illustrated to other settings, including maybe imitation learning and other settings. Okay, so let's consider a very simple case. It's a bandit case. You have 2 players, max player and the min player. Max player wants to maximize reward, min player wants to minimize reward. And each player has 2 actions. Max player has A1, A2, min player has B1, B2. Okay, so let's consider 2 games. In the first game, if max player chooses A1, min player chooses B1, then the reward is 0.5. And if we choose A1, B2, the reward is 1, A2, B1 is 0, A2, B2 is 0.5. And for the second game, we just reach A1, B2 and A2, B1. So we have A1, B1's reward is 0.5, A1, B2's reward is 0, A2, B1's reward is 1, and A2, B2's reward is 0.5. Okay, so if you look at these 2 games, you can see that the Nash equilibrium for game 1 is just A1, B1. So it's actually a pure strategy for both players. So if you look at it, this reason is that remember max players tries to maximize reward. So there's no incentive for max player to choose A2 if min player chooses B1. a mean player, there's no incentive to, given that max player chooses A1, there's no incentive for a mean player to choose B2 because it tries to minimize reward. So this A1, B1 is actually a Nash equilibrium. On the other hand, for the game 2, you can do some calculations, show that A2, B2 is actually the Nash equilibrium because there are no incentive for them, any of them, to change their action. Okay, all right. So that's the two games, and let's consider a data set which just covers A1, B1 and A2, B2. So it does cover the Nash equilibrium in both games, right? Because you do have data from Nash equilibrium. So you have A1, B1, you have also B1, A2, B2. And what your data set is like. So you have a lot of data saying if you choose A1, B1, you get reward 0.5. If you choose A2, B2, you choose reward 0.5 as well. Okay, and here you can also compute the C single. The constant is also upper bounded by it's 2. However, the problem is that if you are given such a data set, you do not know whether you are in game 1 or in game 2 because all you know is that A1, B1 and A2, B2, their reward are 0.5. So in this case, you can only differentiate you're in game 1 and game 2, so you cannot output Nash equilibrium. You don't know whether it's A1, B1 is a Nash equilibrium or A2, B2 is a Nash equilibrium. So that's a counterexample.
Why do you not know that? Don't you see what the players are playing in your data set?
So what you observe is that A1, B1, if you play player 1, max player 1, and mean player B1, you get 0.5, and A2, B2, 0.5.
Okay, but
That's
you look at the rows for A2, B1.
Yeah, exactly. But you may have a data set that only have A1, B1, A2, B2. So if it's basically your point is correct. Like basically you need more information. You need to cover these two parts in order to decide which is the Nash equilibrium. Yeah, that's exactly the point.
Isn't it a common assumption that created that does not know to do more of the action that is better pay?
Yeah, I mean, this is a learning problem. So you need to learn the transition and reward. So here, yes, we are assuming the reward is unknown. So you need to learn it. Yeah.
Could you briefly explain the notation of D-row again?
So D-row is like you have a policy row. And because the environment can be stochastic, so it induces a distribution. So D-row just means the probability mass function or the probability of A2, B2 in this data set that generates a data set.
So,
Or basically in this example, it's just like the behavior policy chooses A2, B2 with probability 0.5.
so complete it depends on the data set. So
It depends. I mean, it's a policy row that generates a data set. So, and this policy will choose A2, B2 with probability 0.5. So, and the distribution is like 0, A2, B2 equals 0.5.
So how do you generate the data set into the?
So the offline setting basically saying you have a policy row and it's interacting with environment and it generates the data. And all you need to do is use that data to compute it. Yeah, the row generates the data with environment. Yeah.
Does such a scenario only arise with pure Nash equilibrium, or can it arise from mixed scenarios as well?
That's a good question. So generally speaking, it's like pure strategy. Yeah. Right. So yeah. So basically the point here, if you have this kind of data set, then it's not sufficient, and you do need some information from A1, B2, and A2, B1. Okay. So what do we need? So this is what we propose. It's called unilateral coverage assumption. Okay. So what we need is that there's a formal definition. Like say, given let's say one Nash equilibrium is mu star nu star, then this assumption requires that this behavior policy or the data set not only covers the mu star nu star, it also covers mu star nu and the mu nu star. Okay, for all mu and nu. Okay, so basically this is the best response. You can also call it best response coverage. So given this mu star, we need to know all the information about what the reward is like for all the other scenarios on the second player. And similarly for mu nu star, given nu star, we want to know all the information for different mu. Okay, so intuitively this corresponds to the left plot. So let's say A1 B1 is Nash equilibrium. We not only need to cover A1 B1, we also need to cover the entire row and the entire column in order to recover this Nash equilibrium. And formally, we say that there exists some, say, unilateral such that for every state action and state action A and action B, then this density ratio between the mu star nu for all nu over this behavior policies, the probability mass this distribution is upper bounded by this constant. So if you do some calculation, you can show that because this holds for all mu and nu, so this C unilateral is at least A plus B. So it's actually bigger than what you need for a single agent setting, and this structurally different. And for the other actions, you don't need to cover them, so it's not the same as uniform coverage. You know, if you use coverage assumption in the two-player setting, basically you need to cover all the action pairs. But actually here it's still weaker than uniform coverage because there are a lot of actions you don't need to cover, at least in this pure strategy case. All right.
Simon, there was another question here in the last couple of minutes.
Okay.
It said, the problem can arise also with mixed Nash as long as that mixed Nash is not fully mixed.
Yeah, that's a good point. So here it's just a one illustrating example for pure strategy. You can clearly see the difference, but if it's a mix, it can also, if not purely a mix, you may say if some action you do not need to mix over, then you can still have the same problem and you still need this kind of assumption. Yeah, that's a good point. All right, so all right, so the actual algorithm for the bandit case is follow a similar paradigm as a single agent case. Basically, we still use pessimism. Okay, so in algorithm, we just first estimate each reward by using the offline data, and we build a confidence interval for each action pair. Okay, so I'll use this R sub bar and R super bar as upper and lower and upper bound for each action pair. Okay. All right, and then you use those lower bounds, just using the lower bounds to compute a Nash equilibrium. Okay, and then you also use the upper bound of all the reward to compute another pair of policies. So this mu sub bar, nu sub bar is the Nash equilibrium computed from this lower bound of the reward, and this mu up bar and nu bar, they are computed. This Nash equilibrium is from the upper bound of the reward. Okay, so here again we are being conservative or pessimism. So for the max player, we'll output the policy computed from the lower bound. So that's why it's also the pessimism. To maximize reward, we use a Nash equilibrium policy for the max player using the lower bound. And for the min player, we use a Nash equilibrium computed using the upper bound for the reward. So that's why for both players, they're still being conservative. All right, so this part is pessimism, and so this for reinforcement learning, you also need to combine with some dynamic programming ideas, but the high level idea is the same. We basically compute the upper and lower bound, and then you're being pessimism. And in terms of some more complexity, we can show that it is A plus B, H cube, say unilateral, or epsilon square. And this is actually tight as well, as there are follow-up work showing this is tight. All right, So that's a two-player zero sum. We can also study the whether we can further relax this condition. And there's one more example showing that it's not possible to relax this condition. So it's a little bit more technical, but you get the idea. So I'll for the time constraint, I'll go on, but basically this assumption is cannot be weakened. All right, so that's for a two-player zero sum. It's a simplest game, and we also want to study like more general game. So in the most general form, it's called multi-agent general sum game. So each agent may have each player, they have their own reward, and now you have say M agent, and you have a joint action space. Each player maximize their own total reward. And here, one important generalization compared with the two-player zero sum case is that here we denote this pi minus I, which is a joint policy of all players except for player I. So this is the most general form of multi-agent Markov games. So again, we want to study what's the offline dataset coverage assumption you need to learn a Nash equilibrium for this general sum game. So here, basically, we show essentially you need the same assumption, but using this generalization of notion pi minus I. So so basically what we need, let's say again, the Nash equilibrium is let's say we have M players. The Nash equilibrium is A1 B1 to say to M. Then the Nash equilibrium, or to find Nash equilibrium, you need the behavior policy covers for this pi. You need to cover for all the agents. So given the policy except given this Nash equilibrium policy except for player I, you need to cover all the policy for I. Okay, so for pi prime and this kind of joint policy in this form. Okay, so basically it's a natural generalization of the two-player zero sum case. Yeah.
You run into an equilibrium selection problem here with there being potentially multiple Nash equilibriums.
So yeah, okay, so that's a great point. So first of all, for general sum game in the offline setting, we only at least here the goal is just to find one of them. So as long as for one of Nash equilibrium you satisfy the condition, you can find it. The problem, in general sum game is that this is a kind of a high dimensional tensor, right? So you may have a if you're like uniform sample from all the actions, then actually the each cell you will have exponentially small probability. So it is possible that the C unilateral is exponentially large. That's definitely possible. So and our bound will also scale with C unilateral. So it does not say violate the exponential lower bound in learning a Nash equilibrium in general sum games. If you have a Curie complexity, there's an exponential lower bound. Yeah. So the idea is similar, like you estimate the volume for each policy of upper and lower bound. It also estimates the best response for the upper and lower bound. And then you're being conservative here. So for the time being, I will just give you the high level idea, which is generalization of two-player zero sum. Here use the best response and the pessimism. And again, in theory, we can show that scale polynomially with the planning horizon, the state space, the number of actions, and this C unilateral coefficient, which can be exponentially large, but in the benign case, it can be polynomially small. And it shows us if the C unilateral is bounded, then this is sufficient. And the bound is not tight, so it's still open whether you get a tight bound here. All right, so the last part I would like to talk about like a structural game. It's called congestion game, okay? So congestion game naturally models like a traffic scenario. Like say you have different roads, you have a number of cars on different roads, and basically you want to assign the optimal like a strategy so that the total utility is maximized. So for example, for this network congestion game, you have three pieces of goods you want to send from the source to the target. Okay, so you have S1 to T1, S2 to T2, S3 to T3. And the action space of this game is the valid path connecting each source to the target. However, if you assign a lot of piece of goods on the same road, then you will incur a higher cost. Okay, that's why it's, getting congested. So it's like you have a higher cost. So the goal in this game is to find the optimal strategy to assign to pick the best path connecting for each of the source and target. That's a congestion game. Yeah.
So this is only a sample complexity result, right? Because that last optimization should be hard even with 2 players.
That's true. Yes, it's yeah, that's a good question. So for the general sum game, our algorithm is not computationally efficient. It is yeah, we require some oracle that can be NP hard. Yes. Yeah, it's still open whether you can have a polynomial time algorithm based on these assumptions. Right, thanks for asking. And yeah, so this is a formal setting for a congestion game. So here you have M players. Okay, so you can think of M player space in this example is M pieces of goods you want to send from source to target. And you have big F facilities. Each facility is just like a road in this map. Okay, and the action for each player or for each piece of goods is like a subset of the facilities. Basically, you're choosing a subset of roads, so you can have a valid path sending from the source to the target. Okay. And the reward here only depends on how many cars, okay, or how many players choose that particular facility. So for a particular facility F, we define this congestion level. Basically, it just counts how many player choose this facility. Okay, and the reward from this particular facility only depends on this count. Okay, so that's the setting. And the total reward for each player is the sum of the reward from each the facility this player chooses. Okay, so that's the idea. All right, so yeah, so basically the model is like if if this one piece of good chooses one path, then you count how many time delay in this path. That's high level idea of this reward. All right, so in this setting, there's some interesting structural properties. So you have 2 kinds of feedback. One is called facility level feedback. So you can observe the delay basically from each road, and the other is called yeah. No, you don't need to assume that, at least in our results. Yeah, but your intuition is correct. Generally speaking, it is in decreasing function. Like so you add more cars on the road, then the cost will increase or the reward will decrease. But here we don't need that property here. Okay, so there are 2 types of feedback. One is facility level feedback, where you get the reward, you see the reward from each facility. That's kind of fine-grained feedback. And the other one is more standard, like agent level feedback, where you can only observe the total reward from each agent. And that's called similar to a unilateral coverage assumption to show that for the second kind of feedback, you only need this unilateral coverage. What's interesting that if you have more fine-grained feedback for the facility level, actually you need a weaker condition to obtain this Nash equilibrium. So this is the final result I want to show. So basically here we define a new constant called C facility. So let me just use this example to show you the idea. So let's say you have 5 facilities. The Nash equilibrium for this game is that you have say 2 cars on facility 1, 3 cars on facility 2, 5 cars on facility 3, 4 cars on facility 4, and 1 car on facility 5. Okay, so this 2, 3, 5, 4, 1. This configuration is say a Nash equilibrium. Let's suppose this is the case. So what our main result shows that what you need is not like a unilateral coverage, which need to change the entire row, entire column. All you need is like a single 1 unit deviation from this Nash equilibrium. So for this configuration, what you need to cover is like you need to cover for facet 1, you also need to observe the reward for 1 car here and 3 cars here. For facet 2, you need to observe the reward for 2 cars here or 4 cars, etc. So in theory, we can show that you only need to cover a little bit more. That's 1 unit deviation from Nash equilibrium in your data set, and that is enough for recover the Nash equilibrium. And sample complex, something like this is say facilities constant times the number of players and number of facilities squared divided by number of data you have.
Is intuition, is this because of monotonicity or something? Or what's the reason that you need kind of less information?
So in this space, it's kind of because now in each here you have more observations. So for each facility, you get 1 observation. So actually the effective dimension, you have more, it's more like a full feedback compared with a banded feedback in online setting sense. All right, so and we'll kind of show like impossibility result, like if you do not have this kind of condition, then you cannot learn a Nash equilibrium. All right, so to complete this talk, basically we show that there's a very interesting structural requirement you need to learn optimal policy or Nash equilibrium from offline data. For single agent, what you need is single policy coverage. You only need to cover the optimal policy. For 2-player zero sum, Nash or general sum, basically you need this unilateral coverage. But if you have some structures in your game, with, for example, congestion game with facility level feedback, you only need a much weaker condition, like a 1-step deviation coverage. In terms of algorithm, the key idea is pessimism, and if you consider the sequential like game setting or reinforcement setting, you just combine it with some standard subroutines in reinforcement learning, like value iteration or policy iteration, etc. And lastly, let me thank my collaborators. Steven Cui is my student, Mariam is my colleague, Hao Zhejiang, who is an undergrad visiting us, and Jihan Xiong is another student from UW. And I would like to conclude here and take more questions.